Imagine flying into a furnace hotter than anything in the solar system and finding it's cooler inside than outside. That's exactly what NASA discovered when Parker's solar probe became the first craft to physically touch the sun. The data that came back broke models, stunned astrophysicists, and revealed bizarre magnetic S-shaped structures whipping through the corona. What's really happening up there changes everything we thought we knew about our star. Tonight, we follow the chain from a 60-year-old prediction to a spacecraft flying inside a living star, until you understand not just what Parker found, but why finding it required humanity to do the impossible. Before we dive in, if you love exploring the secrets of our sun as much as we do, take a second to like the video or subscribe and tell me where you're listening from and what time it is. Now, let's begin. There is a star at the center of everything you have ever known. It is the reason the oceans did not freeze, the reason the first amino acids found enough energy to link together, the reason you are warm right now as you listen to this. You have lived your entire life inside its atmosphere. The outermost whisper of it reaches past Mars, past Jupiter, all the way to the edge of the solar system, where the Voyager probes are still sailing. You have never been outside the sun, not once. None of us have. And yet, for most of human history, we understood it almost entirely from a distance of 93 million miles. We watched it rise and set. We measured its light. We built calendars around its behavior. We even learned, eventually, to decode the nuclear fire at its core. A process so violent and so sustained that every second, the sun converts 600 million tons of hydrogen into helium and releases the equivalent of roughly 10 billion nuclear bombs worth of energy. We knew all of that, more or less, by the middle of the 20th century. What we did not know, what we could not know from 93 million miles away, was what the sun actually felt like up close. What the wind tasted like before it had traveled for days and thinned itself across the vast distances of interplanetary space. What the magnetic field was doing in the few million miles just above the surface, where the corona blazes at temperatures that have no right to exist. We had theories, we had models, we had generations of brilliant physicists who had thought harder about those questions than perhaps any questions in the history of science. But we had never been there. That changed on August 12, 2018, when a small spacecraft lifted off from Cape Canaveral on a Delta IV Heavy rocket and began a 7-year journey inward. The spacecraft was named after Eugene Newman Parker, the first time NASA had ever named a mission after a living scientist. And the choice was deliberate, almost sentimental, because Parker had spent his career being told that his ideas about the sun were wrong. He proposed the solar wind in 1958, when the scientific consensus held that the space between planets was essentially empty. He was laughed at. The two peer reviewers of the journal that eventually published his paper both recommended rejection on the grounds that it was too radical. But the editor, Nobel laureate Subrahmanyan Chandrasekhar, overruled them and published it anyway. Parker turned out to be right, and the solar wind turned out to be one of the most consequential phenomena in the solar system. The probe bearing his name was built at the Johns Hopkins University Applied Physics Laboratory in Laurel, Maryland, and it was designed to answer the questions that Parker himself could never fully resolve from the ground. It would carry 4 instrument suites, measuring magnetic fields, electric fields, plasma waves, energetic particles, and the solar wind itself. And it would carry something else. A heat shield made of carbon composite, 4.5 inches thick, capable of withstanding temperatures approaching 2,000 degrees Fahrenheit, while the instruments behind it remained at room temperature. That shield was the engineering miracle that made everything else possible. Without it, the probe would have been vaporized in minutes. With it, a machine the size of a small car could fly into the atmosphere of a star and take notes. Pause here for a moment, because the sheer improbability of that deserves to sit with you before we go further. AI. Machine the size of a small car, flying through the atmosphere of a star, taking notes, and not only surviving, but functioning normally, transmitting data, completing its mission pass after pass. There is something quietly extraordinary about that image. Something that touches the oldest human impulse, the one that looked up at the fire in the sky and wanted, more than anything, to understand what it was. The cause and effect chain we are going to trace begins long before the launch in 2018. It begins with a mystery that is, in some ways, the most embarrassing unsolved problem in solar physics. A problem so basic, so fundamental, that its continued existence has nagged at scientists for more than 80 years. To understand what Parker found, you first have to understand what Parker was looking for. And to understand that, you have to go back to the surface of the sun itself and ask a question that sounds almost too simple to be worth asking. Why is the corona hotter than the surface? The surface of the sun, the photosphere, the layer that produces the light you see, burns at approximately 10,000 degrees Fahrenheit. That is an almost incomprehensible temperature. Steel melts at around 2,500 degrees. The surface of the sun is 4 times hotter than that. And yet, if you rise just a few thousand miles above the photosphere, a distance that is, in the context of the sun's diameter of 865,000 miles, barely a scratch, the temperature does not fall. It rises, dramatically, impossibly. The corona, the sun's outer atmosphere, reaches temperatures of 1 to 3 million degrees Fahrenheit. In some regions, it may reach 10 million degrees or more. This is, from the perspective of basic thermodynamics, deeply strange. Heat flows from hot to cold. That is one of the most fundamental laws of physics, as certain as gravity, as reliable as the fact that dropped objects fall. If you move away from a heat source, you get colder. That is the rule. The corona breaks the rule. You move away from the surface of the sun, and somehow you get dramatically, almost violently, hotter. Astronomers first began to suspect something strange was happening in the corona in the 1930s. In 1941, the Swedish physicist Bengt Edlén identified spectral lines in the coronal light that could only be produced by iron atoms that had lost 13 of their electrons, a degree of ionization that requires temperatures in the millions of degrees. This was not a theoretical prediction. This was an observation. The corona was, demonstrably, unimaginably hot, and nobody could explain why. The problem became known as the coronal heating problem, and it attracted some of the finest minds in 20th century astrophysics. Wave heating was proposed. The idea that magneto-hydrodynamic waves traveling up from the solar interior could deposit their energy in the corona, raising the temperature. Nanoflare heating was proposed by Eugene Parker himself, beginning in 1987 to 1988. The idea that countless tiny magnetic reconnection events, each releasing a small burst of energy, could collectively heat the corona to the temperatures observed. Reconnection heating, turbulent dissipation, Alfvén wave damping. The proposals multiplied across the decades, each with its champions, each with its critics, none definitively proven or disproven. The fundamental problem was always the same. The corona is too far away, and too thin, and too hot for instruments sitting at Earth's distance to resolve the fine structure needed to distinguish between these mechanisms. You could observe the corona during solar eclipses, when the moon blocked the blinding photosphere and the faint corona became visible. You could observe it with space-based coronagraphs, instruments that artificially created an eclipse. You could build increasingly sophisticated models, but you could not reach in and measure the actual magnetic and plasma conditions in the region just above the surface, the region where, according to most of the heating theories, the critical processes were actually occurring. That is the cause that leads to every effect in this story. The corona heating problem is the original question, the gap in our understanding that is so fundamental, so stubbornly persistent, that building an entirely new class of spacecraft to answer it could be justified on scientific grounds alone. But the corona heating problem was not the only mystery waiting. There was another, older question, one that was also Eugene Parker's, and one that was, in a strange way, even more intimate. Where does the solar wind come from? Parker predicted the solar wind's existence in 1958 based purely on theoretical reasoning. He argued that the corona, this impossibly hot extended outer atmosphere, could not be in static equilibrium. The temperature and pressure at its base were simply too high. The gas had to be expanding outward, continuously, flowing away from the sun at speeds that would eventually leave the solar system entirely. He called this outflow the solar wind. Within a few years, space missions confirmed that Parker was right. The solar wind was real, a continuous stream of charged particles, mostly electrons and protons, flowing outward from the sun at speeds ranging from about 250 miles per second in the slow wind to 500 miles per second or more in the fast wind. By the time it reaches Earth, it has thinned to about 5 to 10 particles per cubic centimeter, nearly a perfect vacuum by any earthly standard, but still carrying enough energy to drive the aurora, to compress the magnetosphere, and occasionally, during major solar storms, to disrupt power grids and satellites. But where exactly did it come from? How did it accelerate from the almost static corona to those enormous speeds? What heated it? What drove it? What gave it the structure it had by the time it arrived at Earth's orbit? These questions turned out to be intimately connected to the coronal heating problem, two faces of the same mystery. Whatever was heating the corona to 1,000,000 degrees was almost certainly also involved in accelerating the solar wind. Solve one, and you likely unlock the other. The answer, or the beginning of the answer, required a spacecraft that could fly into the corona itself, past the region where remote observation became blind, into the zone where the heating and the acceleration were actually happening. The answer required Parker's solar probe. Take stock of where we are. We have a star that has been burning for 4.5 billion years. We have a mystery, the corona's impossible heat, that has resisted explanation for more than 80 years. We have a theoretical framework built by a physicist who was initially dismissed, then vindicated, then honored. And we have a spacecraft built over decades of engineering development, carrying instruments designed to measure phenomena that have never been measured directly, flying closer to a living star than any human-made object in history. Before we follow the probe on its journey, though, we need to understand the physical landscape it was flying into. Because the corona is not simply hot and bright. It has a structure. It has a boundary. And that boundary, largely invisible, impossible to observe remotely with any precision, turned out to be one of the most important physical features of the entire solar system. It is called the Alfvén surface. And understanding it is the key to understanding everything that Parker found. The Alfvén surface is not a surface in any ordinary sense. You could not stand on it. You could not see it. If you flew through it in a spacecraft, as Parker's solar probe eventually did, you would not feel a sudden change in temperature or see a visible line in space. It is defined instead by a ratio. the ratio of the solar wind's outward speed to the speed at which magnetic waves can travel through the solar plasma. When the solar wind is slow, near the sun, magnetic waves travel faster than the wind. Information can propagate back toward the sun. The sun's magnetic field and the solar wind are, in a very real physical sense, still connected. The plasma at this altitude is still, in some meaningful way, part of the sun. As the solar wind accelerates outward, there comes a point, at some distance from the solar surface, where the wind's outward speed exceeds the speed of those magnetic waves. Beyond that point, no information can travel back toward the sun. The magnetic field and the plasma separate. The solar wind becomes its own thing, independent, carrying the sun's imprint, but no longer in contact with it. That transition point is the Alfvén's surface, the true outer edge of the sun, the real boundary between the sun and interplanetary space. Before the Parker Solar Probe, we had no direct measurements of where this boundary was. Theoretical estimates, based on models and remote observations, placed it somewhere between 10 and 20 solar radii from the photosphere, roughly 4 to 9 million miles above the surface. That is an enormous range of uncertainty for such a physically consequential boundary. The difference between 10 and 20 solar radii is the difference between a relatively compact, well-contained corona and an extended, diffuse outer atmosphere that reaches far into space. Parker Solar Probe was designed to cross this boundary. Every Venus flyby, every careful orbital adjustment over the mission's first years, was aimed at gradually shrinking the probe's closest approach to the sun until it dipped inside the Alfvén's surface. When that happened, when the spacecraft found itself inside the boundary for the first time, it would be, in the most literal physical sense possible, inside the sun, part of the sun. Moving through plasma that was still in causal contact with the solar surface, still connected to the processes happening at the base of the corona, still subject to the sun's magnetic field in a way that no instrument at Earth's distance could ever detect. That crossing happened for the first time on April 28, 2021. The spacecraft was on its 8th flyby of the sun. It was approximately 18.8 solar radii above the photosphere, about 8 million miles. And the instruments told a story that nobody had quite expected. The Alfvén's surface was not where the models said it should be. It was not smooth and spherical. It was wrinkled, irregular, full of spikes and valleys, bulging outward in some regions, pulling inward in others. The spacecraft passed through the boundary, not once on that encounter, but multiple times, dipping in and out of the solar atmosphere as it swung around the sun. Each time it crossed, the instruments captured a snapshot of conditions that had never been directly measured: the magnetic field strength, the plasma density, the wave activity, the particle energies, at the very edge of where the sun ends and interplanetary space begins. This was the first major discovery. Not a theoretical prediction confirmed exactly, but something stranger and more interesting. A boundary that turned out to be fundamentally different from what the models had assumed. Not a clean edge, but a dynamic, turbulent, constantly shifting transition zone, shaped by the corona's own complex structure, by the solar cycle, by the distribution of active regions on the solar surface. And within that transition zone, hiding in the data, were the structures that would eventually be named switchbacks. Strange, sharp reversals in the magnetic field, kinks and folds in the field lines that the solar wind was carrying outward. Structures that nobody had predicted, and that, once found, changed the entire conversation about how the solar wind is generated and accelerated. Those structures are where the story gets genuinely strange, and that is where we are going next. The first thing Parker Solar Probe found before it even crossed the Alphen surface, before it had descended anywhere near the depths of the corona, was something nobody had put in the mission's primary science objectives. On November 6, 2018, during its very first close approach to the Sun, still tens of millions of miles from the photosphere, still operating in what scientists considered the outer solar wind, the probe's field's instrument detected something strange in the magnetic field data. The field, which should have been streaming steadily outward from the Sun in a smooth, predictable spiral, was folding back on itself. It was reversing direction, abruptly, sharply, and then, just as abruptly, snapping back to its original direction. The reversal lasted minutes, or sometimes hours, and then it was gone, and the field was streaming normally again as though nothing had happened. These were switchbacks, and they were everywhere. Not one or two anomalies to be filed away and examined later. Not occasional curiosities at the edge of the instrument's detection range. When Parker Solar Probe sent back its first observations from its voyage toward the Sun, scientists found signs of a wild ocean of currents and waves, quite unlike the near-Earth space much closer to our planet. This ocean was spiked with what became known as switchbacks, rapid flips in the Sun's magnetic field that reversed direction like a zigzagging mountain road. The first 4 research papers from the mission were published in December 2019, and the switchbacks were front and center in all of them. They reported the direction and strength of the Sun's magnetic field and described the unusually frequent and short-lived changes in the direction of the Sun's magnetic field. Scientists were not exactly startled that switchbacks existed. The NASA ESA Ulysses mission, which flew over the Sun's poles in the 1990s, had seen hints of similar structures in the distant solar wind. But nobody had anticipated seeing them this frequently, this close to the Sun, this clearly defined. The probe was not yet in the corona. It had not yet touched the Sun. And already the data was strange. Something here deserves attention, because the strangeness of switchbacks is easy to describe, but harder to fully absorb. Imagine the Sun's magnetic field as a set of long elastic threads extending outward from the solar surface, being carried by the solar wind into interplanetary space, gradually unwinding into the large-scale spiral structure first predicted by Eugene Parker himself. Those threads are not rigid. They can twist and bend. But a switchback is not a gentle curve. It is a fold, a hairpin, a sharp S-shaped kink in the field line that doubles back toward the Sun before snapping forward again. Inside the switchback, the magnetic field is pointing sunward. Outside it, the field points away. And as the switchback passes the spacecraft, the probe experiences not just a reversal of field direction, but a simultaneous spike in the solar wind speed, a jet of plasma that is moving significantly faster than the surrounding wind. The two phenomena are consistently coupled. The speed spike and the field reversal arrive together, and they depart together. This coupling was the first clue. It suggested that switchbacks were not simply passive deformations of the field, wave distortions or turbulent folds introduced by the solar wind's own turbulence as it traveled outward. If they were, you would not necessarily expect the speed jets. The speed jets implied that energy was being injected into the solar wind at the switchback's location, that something active was happening inside or around these structures, something that was accelerating the plasma. Scientists think piecing together the story of switchbacks is an important part of understanding the solar wind, the constant stream of charged particles that flows from the Sun. But where were they coming from? Two competing theories emerged almost immediately, and the debate between them illustrates how deeply consequential the question actually is. The first theory held that switchbacks were born in the corona, that they were generated at or near the solar surface, perhaps by magnetic reconnection events, and then propagated outward through the solar wind, carrying their energy with them. Under this theory, switchbacks were a window directly into the processes happening at the corona's base, a signature of the energy that was heating the corona and driving the solar wind, preserved in the field structure as it traveled outward. If this was right, then understanding switchbacks would be equivalent to understanding coronal heating. The second theory held that switchbacks were created in transit, that they were generated not at the sun, but somewhere in the solar wind itself, as the faster and slower streams of wind interacted with each other and folded the magnetic field into kinks. Under this theory, switchbacks were a product of solar wind dynamics rather than a direct signal from the corona. Interesting, certainly, but not the direct window into the corona's heating mechanisms that the first theory promised. The two theories made different predictions about what the probe should observe as it flew closer and closer to the sun. Parker's solar probe observed switchbacks, traveling disturbances in the solar wind that caused the magnetic field to bend back on itself, an as yet unexplained phenomenon that might help scientists uncover more information about how the solar wind is accelerated. When Parker's solar probe sent back its first observations, scientists found signs of a wild ocean of currents and waves quite unlike near-Earth space. This ocean was spiked with what became known as switchbacks, rapid flips in the sun's magnetic field that reversed direction like a zigzagging mountain road. If switchbacks were born in transit, they should become rarer as the probe descended deeper into the inner corona, because at close range, the fast and slow wind streams would not yet have had time to interact and generate the folds. If they were born in the corona itself, they might persist all the way down to the very base of the solar wind, or even intensify as the probe approached their source. The mission's sixth close approach to the Sun, in the autumn of 2020, provided the first major piece of evidence. During the probe's sixth flyby of the Sun, Field's data revealed that the switchbacks aligned with magnetic funnels in the solar surface. These funnels emerge from between structures called supergranules, giant bubbles on the Sun in which hot plasma from the solar interior rises up, spreads out across the surface, cools, and then sinks back down. The magnetic field lines in the gaps between supergranules are concentrated by the convective flow, squeezed together into funnel-shaped structures that extend upward into the corona. And the switchbacks, when their source locations on the solar surface were traced back using magnetic field models, appeared to originate from those funnels. Not from the broad open regions of the solar surface, not from active regions or sunspot groups, from the funnel structures, the junctions between adjacent supergranules. This was a remarkable finding. The magnetic geometry of these regions suggests that magnetic reconnection powers the solar wind. But while the findings locate where switchbacks are made, researchers are still digging into the question of how they're formed. The supergranule funnels are precisely the locations where solar physicists had long suspected that magnetic reconnection, the explosive reconfiguration of magnetic field lines, might be transferring energy into the corona. The alignment between switchback source regions and supergranule funnel structures was not proof that reconnection was creating the switchbacks, but it was a powerful hint. It placed the birthplace of these strange, kinking structures at a location that had independent theoretical reasons to be energetically significant. Pause here, because we are now 3 major discoveries into the mission's early years, and the chain of cause and effect is beginning to clarify. The switchbacks are not random noise in the solar wind data. They appear to originate from specific, identifiable structures on the solar surface. Those structures are associated with the process, magnetic reconnection, that many theorists had long suspected was responsible for coronal heating and solar wind acceleration. And the switchbacks carry energy as they travel outward in the form of those speed jets that accompany every field reversal. The chain from the solar surface to interplanetary space is becoming visible. The question is whether the chain leads back far enough to answer the fundamental mystery, the corona's impossible heat, or whether it is a sideshow, a fascinating phenomenon that points toward the answer without being the answer itself. The mission was not done providing clues, not even close. Consider now the second of the great early discoveries. The solar system is not empty. It is full of dust, an extraordinarily fine, extraordinarily ancient debris field that pervades the inner solar system, the remnants of the collisions and condensations that built the planets 4.5 billion years ago. This zodiacal dust, named after the zodiacal light, the faint glow it produces when sunlit at dawn or dusk, forms a vast, diffuse cloud extending from the outer solar system inward toward the sun. Spacecraft have flown through it for decades. It is a given, a background feature of interplanetary space, as unremarkable in its way as the solar wind itself. Scientists had long predicted on theoretical grounds that this dust could not survive all the way to the solar surface. The sun's radiation is intense. Close enough to the sun, the dust particles would absorb more energy than they could radiate away, and they would heat up until they vaporized. The precise distance at which this vaporization zone began has been calculated many times, with estimates generally placing the inner boundary of the dust-free zone somewhere between 2 and 5 million miles from the solar surface. Scientists had long suspected that close to the sun, this dust would be heated to high temperatures by powerful sunlight, turning it into a gas and creating a dust-free region around the sun. But no one had ever observed it. Nobody had ever gotten close enough to observe it directly. Theoretical predictions and observational confirmation had remained divided by a gap that no earlier mission could cross. The images aboard Parker Solar Probe observed cosmic dust beginning to thin just over 7 million miles from the sun, with that decline continuing steadily to a little over 4 million miles away, the closest range the instrument could reliably measure. By extrapolating this pattern of thinning, scientists predicted a completely dust-free zone beginning roughly 2 to 3 million miles from the sun. The confirmation of the dust-free zone was, in one sense, exactly what the models had predicted. Theory and observation aligned. But it was also something more than a confirmation. It was the first direct measurement of an environment that had been purely theoretical for decades, and it opened the door to questions about what that zone looked like in detail, how its boundaries shifted with the solar cycle, and what the transition from dusty to dust-free space meant for our understanding of the solar system's interior architecture. Parker Solar Probe discovered evidence of a cosmic dust-free zone of approximately 2.2 million miles, 3.5 million kilometers, or about 5 solar radii, in radius from the sun, due to vaporization of cosmic dust particles by the sun's radiation. That vaporization radius was consistent with predictions, but the detail with which the transition could now be characterized, the gradual thinning that began far outside the zone's inner boundary, the fine structure of the dust distribution, was entirely new. On its way toward the sun, Parker began observing higher than expected amounts of dust, greatly improving our understanding of the innermost regions of our heliosphere. It also provided the best direct look yet at the most active region of the zodiacal cloud, a dusty cloud of grains shed from passing comets and asteroids, and offered clear evidence of a dust-free zone around the sun itself. The dust-free zone discovery also carried an implication that reached beyond the solar system itself. Stars like the Sun are common in the galaxy. Many of them, we know from transit observations and radial velocity measurements, harbor planets. The dust distribution in the inner reaches of a stellar system reflects the history of that system's formation. Which collisions happened, which objects migrated, which reservoirs of material were depleted. The fact that Parker could now measure the dust-free zone directly meant that astronomers could, for the first time, anchor their models of inner solar system dust to an actual observation rather than a theoretical extrapolation. That is a small but genuine advancement in our ability to characterize other solar systems by analogy with our own. There was one more early discovery from the mission's first years that deserves careful attention because it connects the switchback story, the Alfvén surface story, and the coronal heating story in a way that the other findings do not. It involves the Sun's magnetic field at the largest scale, the so-called Parker spiral, and a discrepancy in the field's strength that surprised everyone who looked at the data. Eugene Parker, in building his theory of the solar wind in 1958, had also worked out what the Sun's magnetic field should look like as it was carried outward by the wind. Because the Sun rotates once every 25 days at the equator, the field lines being drawn outward by the wind are not straight. They are bent into a spiral shape, like the water from a rotating garden sprinkler, unwinding as they travel outward. By the time the field reaches Earth's orbit, the spiral angle is roughly 45 degrees. This is the Parker spiral, and it has been confirmed by every spacecraft that has measured the interplanetary magnetic field since the 1960s. But when Parker's solar probe measured the magnetic field in the inner heliosphere, inside the orbit of Venus, well within the region that no previous spacecraft had probed in detail, the field was not behaving as the model predicted. It was stronger than expected, significantly stronger, and it was more radially oriented, more directly pointing away from the Sun than a smooth Parker spiral should be at those distances. This stronger, more radial field had implications. A stronger magnetic field in the inner heliosphere meant that the corona's magnetic pressure was playing a larger role in the solar wind's dynamics than the models had assumed. It meant that the process by which the field was transported from the coronal base outward through the solar wind was more complex, more turbulent, more structured than the smooth spiral suggested. And it was consistent with the switchback picture. If the field was being knotted and folded close to the Sun, the average measured field strength would appear elevated because the folds would add an effective radial component that the smooth spiral model did not account for. Some researchers proposed that the stronger field was a direct signature of the very same energy injection that was heating the corona. Others were more cautious, arguing that it might simply reflect the solar wind's own dynamic behavior close to the Sun, where the wind has not yet had time to relax into the smooth spiral geometry that the models described. The debate was unresolved, and it pointed towards something broader, a growing suspicion among the mission team that the inner heliosphere was far more dynamic, far more structured, and far more energetically active than anyone had anticipated before the probe started sending back data. Take stock of where we are now. The mission has yielded 3 major early discoveries: switchbacks, the dust-free zone, and the anomalously strong magnetic field. Each one carries implications for the coronal heating problem. Each one has generated its own body of research, its own competing interpretations, its own unresolved debates. The mission's primary science goal was to determine the structure and dynamics of the Sun's coronal magnetic field, understand how the solar corona and wind are heated and accelerated, and determine what processes accelerate energetic particles. Parker Solar Probe returned a treasure trove of science data that far exceeded quality, significance, and quantity expectations, leading to a significant number of discoveries reported in nearly 700 peer-reviewed publications. And the probe had not yet crossed the Alfvén surface, not yet entered the corona, not yet reached the region where the most consequential measurements would eventually be made. That crossing, and what it revealed, is where the real story begins. On April 28, 2021, during its 8th close approach, Parker Solar Probe finally crossed the Alfvén surface for the first time. The moment itself was not announced in real time. The spacecraft was operating autonomously, far from Earth, and the data only arrived later to be analyzed patiently by the mission team. But when the analysis was complete, the finding was unambiguous. Inside a feature called a pseudo-streamer, the conditions quieted, particles slowed, and the number of switchbacks dropped. A dramatic change from the busy barrage of particles the spacecraft usually encountered in the solar wind. For the first time, the spacecraft found itself in a region where the magnetic fields were strong enough to dominate the movement of particles. The particles were trapped at the sun. These conditions were the definitive proof the spacecraft had passed the Alfvén critical surface and entered the solar atmosphere where magnetic fields shape the escape of the wind. This is worth staying with. The spacecraft was inside the sun's atmosphere, not above it, not orbiting it from a safe distance, inside it. The plasma surrounding the probe was, in a physically meaningful sense, still part of the sun. Information could propagate from the spacecraft's location back to the solar surface through magnetic waves. The field lines were connected. The cause and effect relationship between processes at the corona's base and the probe's location was direct, unmediated by the transition to the free-streaming solar wind that characterizes everything at greater distances. And what the probe found inside the Alfvén surface reframed everything that had been observed before it. During the first pass close enough to cross the boundary, the probe recorded key information about the boundary shape and discovered that rather than resembling a smooth ball, the Alfvén critical surface is wrinkled with spikes and valleys. Sweep established that the wrinkles stemmed from coronal streamers, giant plumes of solar material rising through the sun's atmosphere. Streamers had long been observed by sun-watching spacecraft near Earth, but had never been measured directly. The wrinkled Alfvén surface is not merely an interesting geometrical detail. It carries deep physical consequences. The standard models of the solar corona assumed that the Alfvén surface was roughly spherical, perhaps slightly distorted by the solar cycle and the distribution of active regions, but essentially a smooth, closed boundary. If it was smooth, then at any given distance from the sun, the plasma would either be consistently inside or consistently outside the corona. The physics would be relatively clean. But a wrinkled boundary means that adjacent regions of the solar atmosphere, at the same distance from the sun, can be in fundamentally different physical states. A region sitting above a coronal streamer, where the boundary bulges outward, might be inside the Alfvén surface, still magnetically connected to the solar surface, experiencing the full coronal magnetic pressure. An adjacent region sitting between streamers might be outside the Alfvén surface, already in the free-streaming solar wind. The transition from coronal plasma to solar wind is not a single smooth event happening simultaneously at all longitudes and latitudes. It is a patchy, irregular, constantly shifting process, different in character from one location to the next. This patchiness has consequences for space weather on Earth. The solar wind that arrives at our magnetosphere is not uniform. It comes in streams of varying speed, density, and magnetic field orientation. Those variations drive geomagnetic storms, auroras, and the more dangerous high-energy particle events, that threatens satellites and astronauts. If the variations are seeded at the Alfvén's surface by the irregular wrinkled transition from coronal to solar wind plasma, then understanding the Alfvén's surface's shape and dynamics is directly relevant to predicting the space weather that affects Earth. Science is not purely academic. It has operational stakes. Parker scientists discovered the processes that give birth to the solar wind in the sun's corona. They found evidence that small-scale jetting or jetlets in the corona, driven by a process called magnetic reconnection, is responsible for the heating and acceleration of the solar wind. These mechanisms allow the solar wind to rise through the solar atmosphere, escape the sun's gravity, and permeate the solar system. The jetlets, small-scale ejections of plasma from the corona, driven by magnetic reconnection events at the solar surface, were another piece of the puzzle clicking into place. They were not the grand explosive coronal mass ejections that dominate solar storm forecasting. They were tiny, persistent, ubiquitous. They were happening constantly, all over the sun, in the funnels between supergranules, at the magnetic boundaries where adjacent field systems met and reconnected. And they were injecting energy and mass into the low corona, contributing to the sustained heating that kept the coronal temperature at 1,000,000 degrees and above. The picture that was emerging, slowly, across years of data, across hundreds of published papers, across countless debates at conferences in New Orleans and in journals from the Physical Review Letters to the Astrophysical Journal, was of a corona that was not passively heated by a single dominant mechanism, but actively, continuously energized by a cascade of small events. Reconnection in the funnel structures between supergranules, jetlets rising into the low corona, depositing energy through turbulent dissipation. Alfvén waves propagate upward from the convection zone and dampening their energy in the corona through wave-particle interactions. Switchbacks, born in or near the corona, carrying the imprint of these processes outward into the solar wind. No single process was the answer. The corona appeared to be heated by all of them, simultaneously, with the relative contribution of each mechanism varying by location, by solar cycle phase, by the local magnetic geometry. Some researchers, among them Stuart Bale at the University of California, Berkeley, who led the field's instrument team, began arguing by 2022 that the combination of switchback-related energy injection and magnetic reconnection at the coronal base could account for a substantial fraction of the coronal heating that the models required. Others remained cautious. The quantitative budgets, how much energy each mechanism actually deposited, and whether the total was sufficient to sustain the observed coronal temperature, were not yet closed. They may not be fully closed for years, but something genuinely new had entered the picture. The corona was no longer a mystery that could be dismissed as a problem of remote observation. It had been sampled. Its plasma had been measured, its magnetic field mapped, its wave activity characterized from the inside. The 80-year-old question about why the corona was hotter than the surface was not answered. Not fully, not definitively. But it was now constrained in ways it had never been constrained before. The range of viable answers had narrowed. The mechanisms that could not account for the observed conditions had been eliminated. The ones that remained were the ones most consistent with what a spacecraft inside the sun's atmosphere had actually found. And the probe was not done. With each successive close approach, each orbit tightening slightly, each perihelion bringing the spacecraft a few million miles closer to the photosphere, the measurements grew sharper, the data richer, the surprises more frequent. What lay ahead, at the closest approaches of all in December 2024 and beyond, was still stranger. The story of the coronal holes begins with a deceptively simple observation. Coronal holes are areas where magnetic field lines emerge from the surface without looping back inward, forming open field lines that expand outward and fill most of space around the Sun. They appear dark in extreme ultraviolet images. Dark because they are cooler and less dense than the surrounding corona, because the open field lines allow energy to escape upward rather than trapping it in loops that shine brightly. They have been known since the 1970s, when the Skylab space station returned the first comprehensive extreme ultraviolet images of the Sun and revealed these dark, sprawling regions at the solar poles and at lower latitudes during different phases of the solar cycle. They were understood to be the source of the fast solar wind, the high-speed stream that flows at 400 to 500 miles per second, and that dominates the space environment during solar minimum. But knowing that the fast solar wind came from coronal holes was not the same as knowing how it was produced inside them. The interior of a coronal hole, observed from Earth's distance, appeared relatively uniform, a broad expanse of open magnetic field gently funneling the solar wind outward without any obvious fine structure. The wind, from that distance, seemed to emerge diffusely, as though the hole was simply a leaky region in the Sun's magnetic containment. This was the textbook picture, and it had guided modeling efforts for decades. Parker Solar Probe flew directly through a coronal hole during one of its close encounters, and what it found inside bore almost no resemblance to that diffuse, uniform picture. On June 7, 2023, Stuart Bale of the University of California at Berkeley and James Drake of the University of Maryland at College Park published the results in the journal Nature. The probe had detected streams of high-energy particles that matched the supergranulation flows within coronal holes. Based on the team's analysis, the coronal holes are like showerheads, with roughly evenly spaced jets emerging from bright spots where magnetic field lines funnel into and out of the surface of the Sun. The scientists argued that when oppositely directed magnetic fields pass one another in these funnels, which can be 18,000 miles across, the fields often break and reconnect, slinging charged particles out of the Sun. The showerhead image deserves a moment of consideration. Imagine holding a showerhead above your face, with water, the solar wind, blasting you directly. From that angle, at that distance, the water appears to come from everywhere at once, a uniform spray. But climb up close enough, and you see that it is not uniform at all. It is structured. It emerges from discrete holes, in organized patterns, in focused jets. That is what Parker's solar probe discovered about the fast solar wind. It does not emerge from the hole of a coronal hole. It comes from specific, discrete locations, the funnel structures at the boundaries of supergranules, in focused jets powered by magnetic reconnection. The fact that Parker detected extremely high-energy particles in these jets, tens to hundreds of kilo-electron volts versus a few kilo-electron volts for most solar wind particles, told Bale that it had to be magnetic reconnection, accelerating the particles and generating the Alfvén waves that gave them an extra boost. Reconnection occurs when crossed magnetic field lines snap, explosively flinging away nearby particles at high speeds. In the case of jets and jetlets, the plasma is released in the form of beams along the open magnetic field lines, riding those open pathways out of the Sun's gravitational grip and into the solar wind stream above. This finding closed a loop that had been open since the mission's earliest observations. The switchbacks had been traced back to the funnel structures. The fast solar wind had now been traced back to the same funnel structures. The funnels themselves were powered by magnetic reconnection. And reconnection, the explosive reconfiguration of the magnetic field, releasing stored energy as heat, speed, and waves, was also one of the most favored candidates for coronal heating. The same process, happening in the same locations, was potentially responsible for three separate phenomena that had each been studied independently for decades: the corona's anomalous temperature, the solar wind's acceleration, and the S-shaped switchbacks threading through the inner heliosphere. The big conclusion, as Bale put it, was that it's magnetic reconnection within these funnel structures that's providing the energy source of the fast solar wind. It doesn't just come from everywhere in a coronal hole. It's substructured within coronal holes to these supergranulation cells. It comes from these little bundles of magnetic energy that are associated with the convection flows. Some researchers celebrated this as a near resolution of one of the most durable mysteries in solar physics. Others were more measured. The fast solar wind source within coronal holes appeared reasonably well constrained. But the slow solar wind, the other major component of the solar wind, originating from the boundaries of active regions and helmet streamers at lower solar latitudes, remained more enigmatic. Its source regions were more complex, its connection to specific surface structures more ambiguous. Some researchers proposed that jetlets and small-scale reconnection events were responsible for the slow wind too, but the evidence was less direct, the picture more contested. Analysis of the rate, mass, and energy fluxes of small-scale jetting in the Sun's atmosphere supports the proposal that the ubiquitous small-scale jetting activity, driven by magnetic reconnection, can account for essentially all of the mass and energy lost by the Sun to the solar wind. That is an extraordinary claim, that the continuous small-scale jetting activity, invisible from Earth's distance, unresolvable by any previous mission, is not merely a contributing factor to the solar wind, but its primary engine. The claim has been contested. Some researchers argue that Alfvén wave dissipation plays a comparable or even dominant role, at least in certain regions of the corona. Others suggest that the two mechanisms are deeply entangled, that reconnection generates Alfvén waves, which then propagate upward and deposit additional energy, so that distinguishing between them is somewhat artificial. The debate is ongoing. And that is worth sitting with, because the ongoing nature of the debate is itself a consequence of what Parker's solar probe accomplished. Before the mission, the debate about coronal heating was largely theoretical, a contest between models, each consistent with the available remote observations, none decisively refuted by direct measurement. After Parker, the debate is empirical. It is being fought with data, real measurements from inside the corona, real particle energy distributions from the funnel jets, real wave activity from the field's instrument. The nature of the argument has changed. That, independent of which side eventually wins, is a profound scientific achievement. Step back for a moment and consider the larger picture that is assembling itself. The Sun's surface is covered by convection cells, those supergranules, giant bubbles of rising and falling plasma, each tens of thousands of miles across, each in slow convective turnover. Where adjacent supergranules meet, their downward flows drag the magnetic field into concentrated funnel structures. In those funnels, oppositely directed magnetic field components are driven together by the convective motion. When they meet, they reconnect, explosively, continuously, releasing stored magnetic energy as heat, as plasma jets, as Alfvén waves propagating upward through the corona. Those jets rise through the low corona, depositing energy and mass. Some of them escape entirely, becoming the fast solar wind streams that Parker probe has now directly measured. Others fold the magnetic field as they rise, generating the S-shaped switchbacks that the probe first observed in November 2018. All of this is happening continuously, all over the Sun, in the million or so individual supergranule boundaries active at any given moment. That picture, the Sun, as a vast, continuously churning engine of small reconnection events, each tiny, each brief, but collectively sustaining the corona's million-degree temperature and the solar wind's relentless outflow, is not yet fully proven. But it is the most observationally constrained picture that exists, and it would not exist at all without a spacecraft that flew close enough to resolve the fine structure that all of this depends on. Now the mission was approaching its final closest passes, and the solar environment had changed. The first 4 years of the mission had been conducted mostly during solar minimum, the quiet phase of the 11-year solar cycle when sunspot activity is low, the corona is relatively calm, and major eruptive events are rare. That changed as the mission approached its deepest encounters. By 2023 and 2024, the sun was rising towards solar maximum, the peak of the cycle. When sunspot activity is high, active regions are numerous and complex, and the corona can produce coronal mass ejections and solar flares at far greater frequency. For Parker's solar probe, solar maximum meant something new: the opportunity to measure solar energetic particles, the high-energy particles ejected by solar flares and coronal mass ejections, from inside the corona, closer to their source than any previous instrument had ever operated. Solar energetic particles are one of the most consequential phenomena in space weather. During major solar storms, these particles, primarily protons, but including heavier nuclei, are accelerated to velocities approaching a significant fraction of the speed of light. They can penetrate spacecraft shielding, damage electronics, and deliver potentially lethal radiation doses to unprotected astronauts. Understanding how they are accelerated, what physical process takes a thermal proton from the solar wind and boosts it to energies thousands of times higher, is both a fundamental physics question and a practical problem of enormous importance for future human exploration of deep space. Parker Solar Probe measurements through the narrow shockwaves driven by coronal mass ejections have yielded unprecedented discoveries about the energization of hazardous solar energetic particles. Flying closer to the Sun than any spacecraft before it, Parker Solar Probe uncovered a new source of energetic particles near our star, according to a study published in the Astrophysical Journal Letters on May 29, 2025. The study suggests that magnetic island merging, a process linked to magnetic reconnection, propels particles near the Sun to significantly higher energies, about 1,000 times higher than expected. The lead author, Mahir Desai, of the Southwest Research Institute in San Antonio, summarized the discovery plainly. These findings show that magnetic reconnection in the heliospheric current sheet is a major source of energetic particles in the near-Sun's solar wind. The heliospheric current sheet is the vast, undulating surface that separates regions of opposite magnetic polarity in the solar wind, a structure that extends throughout the entire solar system, like the ruffled skirt of a ballet dancer spinning outward from the Sun. When Parker's solar probe crossed this sheet at close range, it found evidence of magnetic island merging, a specific form of reconnection in which isolated magnetic structures merge together, releasing bursts of energy that accelerate particles to extreme velocities. James Drake of the University of Maryland, a co-author of the 2025 study, put it plainly: "We now, for the first time, have a spacecraft that is going through an enormous magnetic reconnection event and can directly measure everything, and that's simply never happened before." But the 2025 findings about particle acceleration went further still, in a direction that nobody had quite anticipated. A separate study, also published in 2026 in the Astrophysical Journal, examined data from a 2022 encounter when Parker's solar probe passed between the Sun and the site of a magnetic reconnection event in the solar wind. The probe observed a sun-directed jet of particles made of protons and heavy ions. But unexpectedly, analysis of the data revealed that protons and ions were accelerated in different manners. Magnetic reconnection theories had expected these two types of particles to be accelerated in the same way. Instead, the observations showed the protons formed a dispersed beam, like that from a flashlight, while the heavier ions were directed in a straight line like a laser beam. That asymmetry, protons scattering broadly, heavier ions traveling in a tight beam, is not predicted by the standard models of magnetic reconnection. It implies that the reconnection process in the solar wind environment is more complex, more structured at small scales than the theoretical framework had accounted for. The findings will help scientists refine theoretical models of magnetic reconnection to better understand how solar storms are powered. But for now, the asymmetry stands as a demonstration of how much the standard picture still has to accommodate, how many small, specific, observationally grounded details the models must be revised to include. This is one of the most important recurring themes in the Parker Solar Probe data. Not that the big picture is wrong, but that the details of the big picture are far richer, far more complex, and far more surprising than anyone anticipated. The solar wind exists as Parker predicted. It is generated in the corona. Coronal heating is real. Magnetic reconnection is deeply involved. The Alfvén surface marks a real physical boundary. All of these things were known, or strongly suspected, before the mission. What the mission revealed is the fine structure inside each of these phenomena, the grain of the physics, the specifics of the mechanisms, the ways in which the elegant theoretical pictures simplify away a turbulent, structured, continuously active reality. By the time Parker Solar Probe reached its deepest encounters, the record-breaking pass at 3.8 million miles from the photosphere on December 24, 2024, repeated on March 22, 2025, and June 19, 2025. The accumulated dataset from the mission had already produced nearly 700 peer-reviewed publications. It has transformed the field of heliophysics, and it had left a chain of open questions that are, in some ways, more interesting than the questions the mission was designed to answer. The December 2024 encounter was the most closely watched of all. By flying just 3.8 million miles above the surface of the Sun, Parker Solar Probe hurtled through the solar atmosphere at a blazing 430,000 miles per hour, faster than any human-made object has ever moved. The heat shield on the spacecraft's sun-facing side was experiencing temperatures somewhere between 1,600 and 1,700 degrees Fahrenheit. The instruments behind it were working normally at room temperature, collecting data from an environment that no previous machine had ever entered. During this close approach, one of the most striking observations was captured by the Wide-Field Imager for Solar Probe, the WHISPER instrument, built and operated by the Naval Research Laboratory under Principal Investigator Russell Howard. Images captured by Parker Solar Probe as it made its record-breaking closest approach to the Sun in December 2024 have revealed new details about how solar magnetic fields responsible for space weather escape from the Sun, and how sometimes they don't. What WHISPER observed was both beautiful and scientifically significant. During the approach, a coronal mass ejection erupted from the Sun. In the CME's wake, elongated blobs of solar material were seen falling back toward the Sun. This was the solar wind U-turn, a phenomenon that had been theoretically anticipated but never directly observed at such intimate range. The stretched magnetic field lines of the departing CME, as they reconfigured and relaxed after the eruption, were pulling material back toward the solar surface. Inflows, plasma falling sunward, not outward, threading through the corona in the immediate aftermath of a coronal mass ejection. The implications of these inflows are multiple and layered. They show that not all material ejected from the Sun in a CME escapes successfully. Some of it is recaptured, dragged back to the solar surface by the reconfiguring magnetic field, altering the corona's structure and, potentially, influencing the path and properties of the next CME that emerges from the same region. The corona has a memory. What happens in one eruption changes the environment for the next. The Sun is not simply expelling material at random. It is recycling it, reshaping it, through a continuous cycle of ejection and recapture that plays out across spatial scales, too small and temporal scales, too rapid for any previous instrument to resolve. Observations showed how giant solar explosions, called coronal mass ejections, vacuum up dust as they sweep across the solar system, and other observations revealed unexpected findings about solar energetic particles. These observations, from the closest solar approach in history, are still being analyzed. The fourth annual Parker Solar Probe Conference, Parker 4, was held at Johns Hopkins Applied Physics Laboratory in Laurel, Maryland, in May 2025, and highlighted discoveries from all solar encounters, including data from the closest approach on December 24, 2024. Joe Westlake, the director of the Heliophysics Division at NASA headquarters, captured the sense of the moment simply. The data that comes down from the spacecraft will be fresh information about a place that we, as humanity, have never been. That sentence carries weight beyond its directness. Humanity has never been to the surface of the Sun. Humanity has never stood inside a living star's corona. But humanity has now sent an instrument there, an instrument that survived, that measured, that reported back, and the reporting back is still happening. The analysis of the deepest encounter data continues. The surprises continue. The chain of cause and effect that started with Bengt Edlund's spectral identification of million-degree iron in the corona in 1941, that ran through Eugene Parker's theoretical predictions in 1958, that produced the mission launched from Cape Canaveral in 2018, is still propagating forward, still generating new findings, new questions, new revisions to the picture. Something here deserves dwelling on. The chain of cause and effect that leads from the supergranule boundaries on the solar surface to the solar wind arriving at Earth is now, for the first time, observationally grounded at every link. Magnetic reconnection in the funnels, jetlets rising into the low corona, Alphen waves propagating upward and depositing energy. The Alphen surface, wrinkled, irregular, shifting with the solar cycle. The switchbacks threading outward through the inner heliosphere, carrying the fingerprint of the reconnection events that spawned them. The fast solar wind streaming from coronal holes, substructured and organized by the supergranular convection cells it arose from. The energetic particles born from reconnection at the heliospheric current sheet. Each link had been theorized. Each link has now been measured. And yet, the energy budget is not fully closed. The precise fraction of coronal heating attributable to reconnection versus Alphen wave dissipation versus other mechanisms remains quantitatively uncertain. The slow solar wind source regions are still more ambiguous than the fast winds. The full implications of the wrinkled Alphen surface for space weather forecasting are still being worked out. The strange asymmetry between proton and ion acceleration in reconnection events has no satisfying theoretical explanation yet. The corona continues to hold pieces of itself in reserve, not out of obstinacy, but because the physics is genuinely complex, genuinely multi-scale, genuinely dependent on processes happening simultaneously at the scale of supergranule boundaries, at the scale of the full coronal structure, and at the scale of the heliosphere itself. These are not failures of the mission. They are its deepest gift. Picture yourself standing at the edge of a vast ocean at night, with the water glowing faintly beneath you. You came to measure the depth of a single wave. You brought the finest instruments ever built for the purpose. You found the wave, measured it precisely, and in doing so discovered that the ocean beneath it was structured in ways that your deepest diving models had never anticipated. The measurements are real, the structure is real, and the ocean is still largely unexplored. That is where the Parker Solar Probe mission stands as it enters its later years. The instrument is still flying, the data is still arriving, and the questions that remain are not the same questions the mission started with. They are sharper, more specific, more tightly constrained by evidence, which makes them, in a profound sense, more interesting than the broad, open-ended mysteries that motivated the mission in the first place. The cause and effect chain is now observationally grounded at every link we can reach from a spacecraft in the inner heliosphere. But every chain, if you follow it far enough, arrives somewhere unexpected. In the case of the Sun, the chain does not end at the corona. It does not end at the Alfvén surface, or at the fast solar wind, or even at the energetic particles accelerated in the heliospheric current sheet. Follow the chain far enough, backward in time, outward in consequence, and it arrives at Earth, at the magnetosphere that protects life on this planet, at the aurora that brightens the polar skies, at the power grids and satellites and communication systems that civilization depends upon. The Sun and the Earth are connected by the solar wind in a way that is not metaphorical but physical. Material ejected from the Sun's corona arrives at Earth's magnetosphere in 2 to 4 days. Energetic particles from major solar storms can arrive in as little as 8 minutes. The corona's dynamics, those tiny reconnection events in the supergranule funnels, those switchbacks threading through the inner heliosphere, those wrinkled irregularities in the Alfvén surface, propagate outward and eventually arrive here, at the planet where we live, sometimes gently as the aurora and sometimes violently as the geomagnetic storms that have the potential to disable the technological infrastructure of modern civilization. Understanding the Sun, then, is not purely an exercise in satisfying scientific curiosity. It is practical. It has stakes. And what Parker Solar Probe has taught us about the Sun has direct implications for how well we can predict and prepare for the solar events that affect life on Earth. The coronal mass ejection is the Sun's most violent expression. Not a continuous process like the solar wind, not a subtle kinking of the magnetic field like a switchback, but a discrete explosion, a vast bubble of magnetized plasma containing up to 1 billion tons of solar material hurled into space at speeds of up to several million miles per hour. When a coronal mass ejection is directed toward Earth, it can take 1 to 3 days to cross the 93 million miles between the Sun and our planet. When it arrives, it compresses the magnetosphere, drives enormous electrical currents through the ionosphere, and can induce powerful fluctuating currents in long conductors on the ground, power lines, pipelines, railway tracks. The largest recorded geomagnetic storm in history struck Earth in September 1859. The Carrington event, as it is now known, was named after Richard Carrington, a British amateur astronomer who witnessed the solar flare associated with the eruption on September 1st, 1859, from his observatory in Redhill, Surrey, England. The geomagnetic storm that followed was so intense that telegraph systems across North America and Europe failed, and in some cases, the induced currents were so strong the telegraph operators could send messages without their batteries connected. Auroras were visible at latitudes as low as Cuba and Hawaii. A Carrington-scale event today would be devastating. The global power grid, the satellite infrastructure, the communication networks, the GPS systems that guide aviation, shipping, and precision agriculture. All of these are vulnerable to intense geomagnetic storms in ways that the telegraph networks of 1859 were not, because they depend on technologies that are far more sensitive to the induced currents and radiation that extreme solar storms produce. Some researchers have estimated that a Carrington-scale event today could cause trillions of dollars in damage and take years to fully repair. This is why space weather forecasting matters. This is why the ability to predict when a coronal mass ejection will hit Earth, how powerful it will be, and how it will interact with the magnetosphere is more than just an academic concern. It is an engineering and policy priority, acknowledged by governments worldwide and built into the planning of space agencies, power providers, and telecommunications companies. And this is where the science Parker Solar Probe has produced becomes practically consequential, because the forecasting of space weather depends, ultimately, on understanding the processes that generate the events you are trying to predict. If you do not know where the solar wind's fine structure comes from, if you do not understand that its substructure originates in the funnel reconnection events at supergranule boundaries, you cannot build models that accurately represent the wind's properties as it travels from the sun to Earth. If you do not know that the Alfvén's surface is wrinkled rather than smooth, that adjacent regions of the corona at the same heliocentric distance can be in fundamentally different physical states, you cannot accurately model the seeding of solar wind variability that drives the geomagnetic activity patterns at Earth. The space weather implications of Parker's findings are still being worked out. Translating from the fundamental science, the reconnection mechanisms, the switchback origins, the Alfvén's surface structure, to the operational forecasting models that space weather agencies use to issue warnings, is a multi-year process that depends on the full scientific community's engagement with the data. But the foundation is being built. The first layer of the connection between the sun's finest structure and the Earth's technological vulnerability is now observationally grounded in a way it was not before 2018. Consider this chain directly: a supergranule boundary on the solar surface, a feature thousands of miles across, invisible to any telescope before Parker's era of close observation, produces a funnel of concentrated magnetic field. That funnel undergoes magnetic reconnection, generating a jetlet that rises into the corona, and a switchback that propagates outward into the solar wind. The switchback, when it eventually arrives at Earth's orbit 2 or 3 days later, has been modified by its journey. It has interacted with other structures, relaxed partially into the ambient wind, deposited some of its energy. But it still carries the imprint of its origin. It still affects the properties of the solar wind at Earth's magnetosphere boundary. That chain, from supergranule boundary to magnetospheric boundary, is the physical reality that space weather is made of. Parker Solar Probe has illuminated the near-sun portion of that chain for the first time. It has not yet provided the operational forecasting breakthrough that the practical space weather community ultimately needs. That will require additional data, additional modeling, additional mission support. But it has established the physical basis on which that forecasting breakthrough must eventually be built. There is another consequence of the Parker Solar Probe discoveries that reaches further still. Not toward Earth, but toward other stars. Toward the broader question of whether what we have learned about our Sun can be generalized to the billions of other stars in the galaxy. Stars are common. The Milky Way contains something like 200 billion of them, ranging from tiny red dwarfs barely large enough to sustain hydrogen fusion to massive blue supergiants that burn through their fuel in millions rather than billions of years. Most of the stars that potentially harbor habitable planets are similar enough to the Sun, in temperature, in mass, in the basic properties of their magnetic activity cycles, that what we learn about our star has direct implications for what those other stars are doing. Every Sun-like star almost certainly has a corona. Every corona almost certainly has a heating problem. The same fundamental thermodynamic paradox that puzzled Bengt Edlen in 1941, playing out at every G-type star in the galaxy. Every stellar corona almost certainly has an alpine surface, a structured solar wind, a corona heated by processes analogous to those Parker has now observed directly at our Sun. The details will vary. Different magnetic field strengths, different rotation rates, different convection zone geometries will produce different supergranulation patterns, different funnel structures, different reconnection rates. But the underlying physics, the fundamental mechanism, appears to be universal. This matters for the question of habitable planets. The stellar wind from a host star is not merely a background feature of a planetary system. It is an active agent that shapes the atmospheres of planets, that can erode or strip those atmospheres over geological timescales, depending on its intensity and variability. Mars, for example, likely lost much of its early atmosphere to the solar wind, because it lacks the strong global magnetic field that Earth has. And that field is what protects our atmosphere from being gradually sputtered away by the continuous stream of energetic particles from the Sun. Understanding how the solar wind is generated, what controls its intensity, its structure, its variability, is directly relevant to assessing which planets around other stars might retain atmospheres long enough for life to emerge and persist. Younger stars, early in their main sequence lifetimes, tend to rotate faster, and faster rotation drives stronger magnetic activity. Stronger magnetic fields, more frequent and energetic reconnection events, more intense coronal heating, more powerful stellar winds. The young Sun, 4 billion years ago, almost certainly had a much more vigorous corona and a much stronger solar wind than it does today. What that meant for the early Earth's atmosphere, how the strong young solar wind interacted with the early magnetosphere, whether it contributed to or constrained the emergence of life, is a question that the Parker Solar Probe findings help constrain, because understanding the present Sun's corona gives us the physical baseline from which to extrapolate backward in time. Some researchers think that the young Sun's intense solar wind may have played a role in stripping hydrogen from the early Earth, leaving behind the oxygen-rich atmosphere that eventually emerged. Others argue that the early magnetic field protected Earth from the worst of the young solar wind's effects. The debate is ongoing, and it cannot be resolved by Parker Solar Probe alone. But the physical framework that Parker has helped establish, the causal chain from reconnection to solar wind, provides a foundation for modeling the young Sun that did not exist before. Now the mission's deepest findings require the most careful attention. Because what Parker Solar Probe discovered at the innermost reaches of the corona, at 3.8 million miles from the photosphere, inside the Alphen surface, in direct causal contact with the solar surface, was not simply a confirmation of the mechanisms that had been proposed from outside. It was a set of measurements that subtly but fundamentally altered the picture of how the corona works at the smallest, most energetically significant scales. The textbook account of coronal heating before Parker tended to be binary. Either Alphen waves heated the corona, or nanoflare scale reconnection events heated it. Each camp had its data, its models, its adherents. The two mechanisms were treated as competitors, as if the corona had chosen one or the other, and the task of science was to determine which. What Parker found is that the corona did not choose. Both mechanisms operate. They operate together. And, most importantly, they are not independent. The reconnection events in the supergranule funnels generate alphen waves. Those waves propagate upward into the corona and deposit their energy there through wave-particle interactions and turbulent dissipation. The waves, in turn, create conditions that facilitate further reconnection at higher altitudes. The two mechanisms are coupled, driven by the same convective engine, feeding each other, producing a corona that is heated not by one clean process, but by a continuous, multi-scale interaction between wave energy and reconnection energy, with the balance between them shifting by location and by phase of the solar cycle. This is, from a theoretical perspective, a resolution of the debate. But it is the kind of resolution that opens more doors than it closes. If both mechanisms operate and they are coupled, the detailed energy budget of the corona depends on the details of how the coupling works. How efficiently do the reconnection outflows generate alphen waves? How much of the wave energy is deposited in the low corona versus being carried farther outward by the solar wind? How does the coupling change between solar minimum and solar maximum? These are quantitative questions with answers that depend on the fine structure of the corona, the structure that Parker's solar probe has, for the first time, made directly accessible to measurement. The ubiquitous reconnection at small scales serves two purposes: heating the coronal plasma and producing the impulsive jetlets, propelling this plasma into the corona and the solar wind. In magnetic reconnection, a stressed magnetic field stores energy like a twisted rope. During the reconnection, the excess energy is released to the plasma in the form of heat, speed, and waves. In the case of jets and jetlets, the plasma is released in the form of beams along the open magnetic field lines. That sentence, "A stressed magnetic field stores energy like a twisted rope," is worth holding in mind as a physical image, because it captures something essential about the sun's energetics that the corona heating problem, as typically framed, can obscure. The corona is not anomalously hot because it is being heated by some exotic external process. It is hot because the sun's convection zone continuously stresses the magnetic field, twisting it, folding it, driving opposing field regions together. And the field's response to that continuous mechanical stressing is to release energy, as heat, as particle jets, as waves. The corona is not a mystery in the sense of requiring unknown physics. It is a consequence of known physics playing out at scales and intensities that were, until Parker, inaccessible to direct measurement. That reframing is subtle but important. The coronal heating problem was never a problem of missing physics, a gap where new laws of nature would need to be inserted. It was always a problem of inaccessible physics, processes happening too close to the sun, at too small a scale for remote observation to resolve. Parker's solar probe did not solve the problem by discovering new physics. It solved it, partially, provisionally, with important details still contested, by going there, by being in the place where the physics was happening and measuring it directly. There is something quietly profound in that distinction. The universe does not withhold its secrets because it is operating by rules we do not yet understand. It withholds them because we have not yet been close enough to see. The heliospheric current sheet deserves its own extended treatment because it is one of the largest and most physically consequential structures in the entire solar system, and Parker Solar Probe's crossings of it, close to the Sun, have produced some of the most surprising data of the entire mission. Picture the Sun's global magnetic field, not the fine structure of funnels and loops, but the large-scale field that extends outward through the entire heliosphere. At any given moment, the Sun has a north magnetic pole and a south magnetic pole, broadly analogous to Earth's, though far more complex in its local structure and far more variable over the solar cycle. The field from one polarity hemisphere and the field from the other must meet somewhere at some boundary, because both fields fill the same solar system. That boundary, the thin, undulating sheet where the north polarity magnetic field from one solar hemisphere meets south polarity field from the other, is the heliospheric current sheet. It is not flat. It is not spherical. It undulates as the Sun rotates, rippling outward through the solar system in a shape that has been compared to a ballerina's spinning skirt or to the surface of a crumpled piece of paper slowly rotating in space. At Earth's orbit, the sheet passes by regularly as the Sun rotates, and each passage can bring a change in the solar wind's properties, and, occasionally, a geomagnetic disturbance as the magnetosphere responds to the changing field orientation. Parker Solar Probe crosses this sheet at close range, inside the orbit of Venus, where the sheet is thinner, more structured, and more energetically active than it is farther from the Sun. The crossings have been scientifically remarkable because the current sheet close to the Sun is a site of intense magnetic activity, precisely the kind of environment where magnetic reconnection occurs naturally, where magnetic island structures form and merge, and where energetic particle acceleration can happen with great efficiency. The 2025 study by Mihir Desai and colleagues at the Southwest Research Institute, published in the astrophysical journal Letters, focused specifically on these near-Sun current sheet crossings. Using Parker data, the study suggests that magnetic island merging, a process linked to magnetic reconnection, propels particles near the Sun to significantly higher energies, about 1,000 times higher than expected. The heliospheric current sheet, long known as a structurally important feature of the solar system, turns out to be an active particle accelerator operating continuously in the inner heliosphere, a discovery that has significant implications for understanding how solar energetic particles reach the dangerous energies at which they pose a hazard to spacecraft and astronauts. The mechanism is specific and worth explaining. Magnetic islands are isolated, roughly circular structures in the plasma where magnetic field lines close on themselves, regions where the field topology has been modified by reconnection events, creating a contained pocket of plasma and field that is distinct from the surrounding medium. When two magnetic islands approach each other in the current sheet, they can merge, a process that is itself a form of reconnection, releasing the energy stored in both islands simultaneously. The merging process accelerates particles caught between the islands to energies far higher than the reconnection at a single small scale would produce. Multiple merging events, occurring in sequence, can boost particles to energies approaching those associated with major solar flares. These findings indicate that magnetic reconnection in the heliospheric current sheet is an important source of energetic particles in the near-Sun solar wind. That finding matters because it identifies a previously unrecognized particle acceleration mechanism operating continuously in the inner heliosphere, not just during the dramatic observable eruptions of major solar flares and coronal mass ejections, but as a steady background process, contributing a continuous low-level flux of energetic particles to the near-Sun environment. For space weather, this matters in a subtle but real way. The energetic particle environment near the Sun is not simply the sum of large discrete events. It has a continuous structured background contribution from current sheet crossings, a contribution that was invisible before Parker probe flew close enough to measure it directly. Through all of this, Through the switchbacks and the funnel jets and the wrinkled Alfvén surface and the current sheet crossings, there is a single physical concept that keeps returning to the center of the picture. It is magnetic reconnection. It appears in the funnel heating. It appears in the switchback generation. It appears in the fast solar wind acceleration. It appears in the energetic particle production at the current sheet. It is, increasingly, the unifying physical process, the mechanism that the sun uses, repeatedly and at every scale from supergranule funnels to the global heliospheric current sheet, to convert stored magnetic energy into the thermal, kinetic, and particle energies that characterize the corona and the solar wind. Magnetic reconnection is not new. It was proposed as a physical process beginning in the early 1950s by British physicist James Dungey, with his landmark paper on how Earth's magnetosphere could be breached by the solar wind through reconnection of terrestrial and interplanetary magnetic field lines, published in 1961. It was subsequently recognized as a fundamental process in plasmas throughout the universe, operating in laboratory fusion experiments, in planetary magnetospheres, in stellar flares, in the jets of active galaxies. Parker Solar Probe has not discovered magnetic reconnection. What it has done is establish, through direct measurement inside a stellar corona for the first time in history, that reconnection is the primary mechanism by which a specific star, our Sun, maintains its corona and drives its solar wind. That is a quantitatively and observationally grounded statement, in a way that all previous discussions of reconnection's role in coronal heating were not. It is grounded in the specific, measured particle energies in the funnel jets. It is grounded in the observed alignment between switchback source regions and supergranule funnel structures. It is grounded in the measured properties of the heliospheric current sheet crossings and their associated energetic particle populations. Each of these measurements constrains the reconnection hypothesis in ways that remote observation never could. Some researchers have argued, and they continue to argue, that this picture remains incomplete, that the role of Alfvén waves in coronal heating is being underweighted by the reconnection-centric interpretation of Parker's data. Their position is that the reconnection events and the Alfvén waves are so intimately coupled that attributing primacy to either one is somewhat artificial, that the corona is heated by a turbulent cascade in which both play essential roles, with reconnection providing the initial energy injection and wave turbulence distributing that energy through the plasma at fine scales. This interpretation is not inconsistent with the data. It is a different emphasis within the same broad picture, and it will likely take additional targeted observations and possibly additional missions to definitively determine the relative energy budgets. What is not in dispute is the physical landscape that Parker has revealed. The solar surface churning with convective flows, the supergranule boundaries concentrating and stressing the magnetic field, the funnel structures where opposing field components are driven together, the reconnection events releasing energy as heat, jets, and waves, the low corona populated by rising jetlets and propagating Alfvén waves, the Alfvén surface, wrinkled and dynamic, marking the outer edge of the magnetically connected corona, the solar wind, substructured and organized, carrying the fingerprints of its origin all the way to Earth's orbit and beyond, and threading through all of it, the switchbacks, those strange S-shaped kinks in the magnetic field, now understood to be born in the funnel reconnection events at the solar surface, propagating outward as emissaries of the corona's activity, eventually arriving at Earth's magnetosphere and contributing to the geomagnetic variability that affects human civilization. That landscape is the most detailed and observationally grounded picture of the Sun's near environment that humanity has ever possessed. It will be revised. it will be extended. The questions it raises will motivate new missions, new theoretical frameworks, new generations of scientists who will push the understanding further. But it will not be unlearned. The corona is not mysterious in the way it once was. Not because the mystery is fully solved, but because the mystery is now empirically constrained in ways it was not before a small spacecraft, protected by 4.5 inches of carbon composite, flew into the atmosphere of a star and survived. There is one more piece of the picture that the mission has illuminated, and it is perhaps the most practically consequential of all. The question of what happens to the solar wind between its birth in the corona and its arrival at Earth. The solar wind does not simply blow outward from the sun in a smooth, uniform stream. It is structured, it is variable, it interacts with itself. And the nature of that interaction, the way in which different solar wind streams overtake each other, merge, create shocks and boundaries, is one of the primary drivers of the geomagnetic activity that produces both the aurora and the more dangerous, grid-threatening storms. Parker Solar Probe, by measuring the solar wind at its closest approach to the sun, has provided the most direct observation ever obtained of what the wind looks like before it has had time to be processed by the interactions that occur during its 2 to 4 day journey to Earth. The solar wind near the sun, close to its source, is substantially more structured, more variable, and more energetically active than the solar wind at Earth's orbit. The switchbacks, which are abundant close to the sun, become rarer at greater distances as the wind propagates outward and the structures gradually relax into the ambient flow. The strong radial magnetic field that Parker measured in the inner heliosphere, stronger and more radial than the models predicted, relaxes into the Parker spiral geometry by the time it reaches Earth. This near-sun baseline is scientifically invaluable because it allows researchers, for the first time, to track the evolution of specific solar wind structures as they travel from their source to Earth. Before Parker, the solar wind at Earth's orbit was measured in detail by instruments aboard numerous spacecraft. The WIND spacecraft, the Advanced Composition Explorer, the DS-COVR satellite positioned at the L1 Lagrange point. But none of those spacecraft could see the wind at its source. They could only measure what arrived after days of travel, after all the interactions and modifications of the interplanetary journey had already occurred. With Parker's measurements at the source and the L1 measurements at the destination, researchers can now, in principle, trace a specific solar wind structure from its origin to its arrival at Earth. That is a capability that space weather forecasting has needed for decades. The ability to connect cause and effect across the 93 million miles of the inner solar system. The practical challenge is that the journey from source to destination is not deterministic. The solar wind's evolution is turbulent, non-linear, sensitive to initial conditions in ways that make precise prediction inherently limited. The best that science can realistically offer for the foreseeable future is not an exact prediction of what a specific solar wind structure will look like when it arrives at Earth, but an improved statistical characterization of the relationship between near-sun conditions and Earth orbit outcomes, a better prior, a tighter probability distribution, a more informed forecast. That improvement is not trivial. In the context of space weather preparedness, the difference between a forecast that warns of a possible major storm with a wide range of uncertainty and a forecast that specifies the storm's intensity and arrival time with greater precision could mean the difference between an unnecessary power grid shutdown and a timely, targeted protective action. Parker Solar Probe's near-sun measurements are a foundational contribution to that improved forecast capability. Even if the translation from fundamental science to operational product will take years of additional work, stand at the edge of something for a moment. Not a physical edge, not a cliff or a shore, but the edge of what can be known from a single vantage point. Parker's solar probe has traveled closer to the Sun than any human-made object in history. It has measured the corona's magnetic field, its plasma density, its wave activity, its particle populations, its reconnection events, its dust boundaries. It has crossed the Alphen surface and reported back from inside the Sun's atmosphere. It has done everything it was designed to do, and many things nobody designed it to do. And yet, standing here with all of that data, all of those nearly 700 peer-reviewed papers, all of those revised and constrained and partially answered questions, there is a feeling not of conclusion, but of arrival at a new threshold. The threshold is not a failure of the mission. It is the natural consequence of what genuine scientific progress looks like. Every answered question reveals two unanswered ones. Every measurement that constrains a mechanism reveals the mechanism's next layer of complexity. The corona is hotter than the surface. We now know, with observational confidence, that magnetic reconnection in supergranule funnel structures is a primary driver of that heating, and that Alphen waves propagating upward from those same reconnection events carry additional energy into the corona. We know the Alphen's surface is wrinkled, dynamic, shaped by the solar cycle. We know the fast solar wind is substructured within coronal holes, organized by the supergranular convection cells from which it emerges. We know switchbacks are born near the solar surface, not in transit, and carry the fingerprints of the reconnection events that produced them. These are genuinely new things to know. They were not known before 2018. They are grounded in direct measurement rather than theoretical inference. They will not be unlearned. And still, the energy budget is not fully closed. The precise coupling between wave heating and reconnection heating remains quantitatively uncertain. The slow solar wind's fine-scale source structure is less clearly resolved than the fast winds. The wrinkled Alphen surface's implications for space weather forecasting are still being computed. The strange asymmetry between proton and ion acceleration in reconnection events has not yet received a satisfying theoretical explanation. These are not small loose ends. They are genuine open frontiers, defined by observation, waiting for the next generation of instruments and ideas to push through. This is the cooling valley of the story, not a disappointment, a breath. A moment to take stock of the landscape before the final ascent. Picture yourself inside the corona itself, not metaphorically, but in the most literal sense the imagination can sustain. You are 3 million miles above a surface burning at 10,000 degrees Fahrenheit. The heat shield between your instruments and the sun is experiencing 1,700 degrees on its face. Behind it, protected by the most carefully engineered thermal barrier ever carried into space, the instruments are running at room temperature, quietly counting particles, measuring field vectors, recording wave amplitudes. Around you, the plasma is unlike anything in ordinary human experience. It is extraordinarily thin, far thinner than the best vacuum achievable in any laboratory on Earth. But it is not empty. It is a continuous fluid of charged particles, electrons, and protons streaming through a magnetic field whose topology is constantly being stressed and reconfigured by the convective motion of the solar surface below. The field lines are not static. They are being continuously dragged, twisted, pushed together, broken, and reconnected. Every reconnection event releases a small burst of energy, a tiny explosion, invisible to any human sense, but measurable by an instrument in its precise location. You are inside a magnetic weather system of extraordinary complexity, one that has been operating continuously for 4.5 billion years. The reconnection events happening around you are not occasional anomalies. They are the normal state of affairs. They are what the corona is, fundamentally, a plasma held in a state of continuous, driven energetic activity by the mechanical power delivered from below by the convection zone, power that cannot be held in place and must be continuously released. The corona does not heat itself despite the laws of thermodynamics. It heats itself because of them. The energy had to go somewhere. This is where it goes. The temperature rises as you move outward from the photosphere below you. It rises because the energy being released by the reconnection events and deposited by the Alf-Venn waves is distributed through the coronal plasma faster than the plasma can radiate it away. The corona is optically thin. It cannot efficiently radiate its energy as visible light. So the energy accumulates, driving the plasma temperature to the extraordinary values that Bengt Edlund first identified in those spectral lines in 1941. What he saw was not a violation of physics. It was physics doing what physics does, playing out in an environment whose fine structure was too small, too close to the sun, too physically extreme for anyone at his time to observe directly. Now we have observed it. The observation took 7 years of spacecraft development, a 7-year mission, 24 close encounters, and the engineering ingenuity to build a heat shield that could survive the corona's edge. But the observation has been made, and what it reveals, at the most fundamental level, is not a strange exception to the universe's rules. It is those rules operating in an environment we had not yet been able to see. Stay with that for a moment. The corona's million-degree temperature, which looked for 80 years like an anomaly, turns out to be a consequence. A consequence of convection. A consequence of magnetic field topology. A consequence of the plasma physics of reconnection, operating at scales that range from the 18,000-mile funnel structures in supergranule boundaries all the way down to the electron and ion gyration scales, where the actual energy transfer ultimately happens. The coronal heating problem is not mysterious in the sense that black holes or dark matter are mysterious. It does not require new physics. It required proximity. It required a spacecraft that could be there. The question of what we cannot know, not merely what we do not yet know, but what is in principle inaccessible from any measurement we can currently conceive, is worth dwelling on before we go further. Because the Parker Solar Probe story, as remarkable as it is, has a boundary. A limit beyond which the chain of cause and effect becomes opaque, not because the physics stops, but because the measurement becomes impossible. That boundary is the photosphere itself. Parker Solar Probe has reached 3.8 million miles above the photosphere. At that distance, it is inside the Alf-Venn surface, inside the magnetically connected corona, measuring plasma that is still in causal contact with the solar surface. But it has not approached the photosphere. It has not measured the convection zone directly. It has not sampled the reconnection events at the very base of the funnel structures in the first few hundred miles of the corona, where the energy injection from below is most intense and the plasma conditions are most extreme. Can we ever reach that close? Possibly not. The thermal environment within a few 100,000 miles of the photosphere, where the corona's temperature is rising steeply, where the radiation pressure from the photosphere itself is intense, where the density of the plasma creates additional heating challenges for any spacecraft, may lie permanently beyond the reach of instrumentation that must survive long enough to take measurements and transmit them. There are proposals in the long-term roadmap of heliophysics for missions that could reach closer than Parker. But the engineering challenges scale faster than linearly with decreasing perihelion distance, and the region immediately above the photosphere may represent a permanent observational boundary, a place that can be modeled, can be inferred, but cannot be directly sampled. There is also a second limit, more fundamental, less engineering dependent. The fine structure of the corona, at the very scales where the energy transfer between the magnetic field and the plasma ultimately occurs, happens at the plasma kinetic scale, the scale of individual particle gyration in the magnetic field, measured in tens to hundreds of meters. This is a scale at which no instrument that fits aboard a spacecraft can make direct measurements. The instruments aboard Parker probe measure bulk plasma properties, average velocities, temperatures, field strengths, wave amplitudes, at scales of kilometers to thousands of kilometers. The final steps in the energy cascade, from macroscopic wave energy and reconnection energy to the microscopic thermal motion of individual particles, happen at scales that are observationally inaccessible from any macroscopic instrument, by any physical spacecraft we can currently imagine building. We cannot know from direct measurement precisely how the energy moves from the alphen wave scale to the electron thermal scale. We can infer it, we can model it, we can constrain the models with the macroscopic measurements Parker has provided. But the final steps are invisible to the instruments we have built. They are, in the current state of measurement technology, beyond the reach of direct observation. Not because the universe is hiding them, but because the scales involved are simply too small for the instruments we can carry. This is not a temporary limitation waiting to be overcome by a more ambitious mission. It may be a permanent feature of what is empirically accessible. What does this mean for the coronal heating problem? It means that even a fully successful Parker Solar Probe mission, even a mission that precisely constrains the energy injection from reconnection and waves at macroscopic scales, cannot close the energy budget by direct measurement all the way down to the thermal scale. The final accounting will always depend at some level on theoretical models of plasma kinetic physics that are anchored by observation, but not directly confirmed at the smallest scales. The coronal heating problem, fully solved, will always have a theoretical component that observation can constrain, but never fully replace. That is an honest admission about the limits of what the mission can achieve. And it is, in a strange way, one of the most scientifically valuable things that Parker Solar Probe has given us, a precise, observationally grounded definition of where our knowledge ends and our models begin. What does it mean for a star to be alive? Not alive in the biological sense, not reproducing, not metabolizing, not subject to natural selection, but alive in the sense of being continuously, dynamically active, of possessing a complex internal structure that sustains itself far from equilibrium, of interacting with its environment in ways that are not predictable from its average properties, but depend on its detailed, constantly changing internal state. The Sun, as Parker Solar Probe has revealed it, is alive in exactly this sense. It is not a steady, passive radiator of light and heat, the reliable background against which Earth's drama plays out. It is a dynamic system, its surface churning with convective cells, its magnetic field continuously stressed and released, its corona maintained at million-degree temperatures by a cascade of small, persistent energy injection events that never stop. The solar wind it produces is not a smooth outflow, but a structured, variable, switchback threaded stream that carries the signature of every small reconnection event occurring on the solar surface. The Sun's dynamism has been known in broad strokes since the discovery of sunspots, of solar flares, of coronal mass ejections. What Parker Solar Probe has added is the fine grain, the specific mechanism by which the solar surface's convective energy finds its way into the corona, the precise spatial structure of the solar wind's source regions, the detailed properties of the boundary between the connected corona and the free streaming wind. It has added the texture that was previously invisible. And that texture matters, not just scientifically, but philosophically, because the sun's texture is the texture of the space around us. The near-Earth environment, the magnetosphere, the ionosphere, the region of space where satellites orbit and where future astronauts will travel to and from the Moon and Mars, is not a passive void. It is the active, variable product of a star's continuous interior dynamics. We live inside the sun's atmosphere. We always have. And the question of how well we understand the sun is ultimately the question of how well we understand the environment in which civilization must survive and expand. Consider what Parker's solar probe accomplished in terms of the human timeline that produced it. Eugene Parker published his solar wind paper in 1958. The mission bearing his name was approved in principle in the fiscal year 2009 budget. It launched in 2018. It completed its primary mission in 2025. The total time from theoretical prediction to direct observational confirmation of the solar wind's fine-scale origin, 67 years, 3 generations of scientists. The lifetimes of entire research careers, from graduate school to emeritus status, spent working on pieces of the problem without ever knowing whether the answer would arrive in their lifetime. Parker himself lived to see the mission launch. He died in March 2022 at the age of 94, having witnessed the first crossing of the Alphen surface, the boundary he had theorized in 1958. And having seen the first data from inside the corona he had spent his career studying. He lived long enough to know that the wind he predicted was real, that the mechanism he suspected was observationally supported, that the star he had devoted his intellectual life to understanding was, in the end, comprehensible. That is a rare gift in science. Most of the fundamental questions in physics and astronomy outlast the people who first posed them. The coronal heating problem was posed by observers who saw the spectral lines of highly ionized iron in the 1930s and 1940s. They are long gone. The problem they identified has now been substantially, though not fully, answered. Answered not by theoretical insight alone, but by the physical act of going there. By building something that could survive the fire and measure it from inside. There is an old question in the philosophy of science about what it means to explain something. To explain the corona's temperature, is it sufficient to identify the mechanism, magnetic reconnection, Alphen waves, without being able to trace every joule of energy through every scale of the cascade? Is a partial, constrained, observationally anchored explanation the same kind of knowledge as a complete, closed, every scale accounted for explanation? The answer probably depends on what you are trying to do with the explanation. For space weather forecasting, a partial explanation that correctly identifies the dominant mechanisms and constrains their relative contributions may be sufficient for practical purposes. For fundamental physics, the open questions at the kinetic scale remain genuinely important. But for the human impulse that originally motivated the question, the impulse that looks at the sun and wonders why it is the way it is, the answer Parker's solar probe has provided is deeply, substantially satisfying. The corona is hot because the sun's convective interior continuously stresses the magnetic field, driving reconnection and wave generation in the funnel structures between supergranules, releasing stored magnetic energy as heat, jet, and wave in a cascade that maintains the corona at temperatures that, from 93 million miles away, look like a thermodynamic impossibility. That is not a complete answer. But it is a true one, and it was not known, with observational grounding, before 2018. The Sun is about 4.5 billion years old. It is expected to burn for roughly another 5 billion years before exhausting its hydrogen fuel and beginning its transformation into a red giant, eventually casting off its outer layers as a planetary nebula and leaving behind a white dwarf, a dense, slowly cooling remnant roughly the size of Earth. Human civilization, at most a few 100,000 years old, occupies only a tiny fraction of the Sun's total lifespan. The period of scientific observation of the Sun, perhaps 4 centuries since Galileo first pointed a telescope at it in 1610, is still smaller. And the era in which humanity has been able to reach out and touch the Sun, to send an instrument into its atmosphere and measure what is there, began on April 28, 2021, when Parker Solar Probe crossed the Alfvén surface for the first time. That era is 4 years old, 4 years out of 4.5 billion. The fraction is so small it has no useful analogy. It is, in the cosmic timeline, the last fraction of a second before midnight. We are at the very beginning of our direct relationship with the Sun. The Parker Solar Probe mission is not a conclusion. It is a first expedition, the first time a human artifact has entered a stellar atmosphere and survived, the first direct measurement of the processes that heat a star's corona and drive its stellar wind. It is the equivalent, in the history of solar exploration, of the first ship that crossed the Atlantic and brought back reports of what lay on the other side. It changed the map. It did not exhaust the territory. What lies ahead? In the next decades of heliophysics, in the missions that will be motivated by Parker's findings, in the theoretical work that will use Parker's measurements as constraints, is a deeper, more complete, more quantitatively precise understanding of the Sun's dynamics. The energy budget will be closed more tightly. The slow solar wind source structure will be resolved more clearly. The coupling between wave heating and reconnection heating will be quantified more precisely. The implications for space weather forecasting will be translated into operational practice. The lessons for stellar physics and the habitability of exoplanetary systems will be worked through in detail. And along the way, almost certainly, there will be surprises. The inner heliosphere has already demonstrated that it has a capacity for strangeness that exceeds what any model predicted. The switchbacks, the wrinkled Alfvén surface, the particle acceleration asymmetry between protons and ions. The surprises did not stop when the data became richer. They became more specific, more detailed, more physically consequential. The next generation of instruments, flying closer or measuring with greater resolution, will almost certainly find new strangeness waiting. That is the nature of the enterprise. That is what it means to genuinely explore a place that no instrument has been before. You do not find what you expected. You find what is actually there. There is one more thing worth saying before this story arrives at its close, and it concerns the relationship between distance and understanding. We have been watching the Sun for all of recorded human history. We have built calendars around it, worshipped it, feared its eclipses, and celebrated its return after the winter solstice. We have analyzed its light with spectroscopes since the 19th century, decomposing its radiation into the spectral lines that reveal its composition, its temperature, its magnetic field. We have watched it from space since the 1960s, with instruments capable of seeing wavelengths of light that the Earth's atmosphere blocks, the X-rays and ultraviolet radiation that reveal the corona's structure and activity. We have built increasingly sophisticated models, run increasingly detailed numerical simulations, devoted enormous intellectual resources to understanding the star that makes our planet habitable. And yet, after all of that, after all the spectroscopy and modeling and space-based observation, the answers to the most fundamental questions about the Sun's corona waited for a spacecraft to simply go there. Distance is not merely a physical obstacle. It is an epistemic one. The Sun, at 93 million miles, is a different object, epistemically, from the Sun at 3 million miles. Not because the physics is different. The physics is the same at both distances. But because the scales you can resolve, the structures you can distinguish, the processes you can directly sample, these change dramatically with distance. The coronal heating problem was not solved by cleverer analysis of distant data. It was solved, partially and with important work remaining, by the physical act of closing the distance, by going there. This is a lesson that extends beyond solar physics. It is a lesson about the limits of remote sensing and the irreplaceable value of in situ measurement, of being in the place where the phenomenon occurs, rather than inferring it from the signal that propagates out to your detector at a safe remove. It is a lesson about the necessity of exploration, physical, actual, instrument-carrying into harsh environment exploration, as a complement to theoretical progress. The Sun has been 93 million miles away for all of human history. For 4 years, we have had an instrument inside it. The difference in what we know is not proportional to the change in distance. It is far greater. Because the processes that matter most, the reconnection events in the funnel structures, the fine-scale structure of the Alfvén's surface boundary, the particle dynamics in the heliospheric current sheet, were simply not accessible from 93 million miles away, regardless of how sophisticated the instruments were. They required proximity, they required contact, they required touch. And touch, in the vocabulary of space exploration, means sending a machine into the fire and trusting that it will survive and report back. Parker Solar Probe did that. It did it 24 times at its record-breaking closest approach distance. It did it with all 4 instrument suites functioning normally. It did it in an environment where temperatures approached 2000 degrees Fahrenheit on the heat shield's face, and room temperature prevailed behind it. It did it faster than any human-made object has ever moved, 430,000 miles per hour, fast enough to travel from New York to Los Angeles in about 20 seconds. That is, by any measure, one of the most extraordinary achievements in the history of space exploration. Not because of the speed or the temperatures survived, though those are remarkable, but because of what the proximity made possible. Because of what was learned by being there, inside the atmosphere of a star, measuring the processes that sustain it from the only position from which those processes could be measured. The Sun will rise tomorrow. It will rise the day after that, and for approximately 5 billion more days beyond that, long after any trace of human civilization has dissolved into the geological record of the small blue planet orbiting it at 93 million miles. It will do what it has always done: churn its convective interior, stress its magnetic field, release that stress through reconnection and waves in the supergranule funnels, heat its corona to temperatures that dwarf anything on the planetary surfaces it illuminates, and send its wind outward through the solar system, threading through the magnetospheres of all the planets, carrying the Sun's magnetic fingerprint to the very edge of the heliosphere, where the Voyager probes are still sailing through interstellar space. All of that was happening before we understood it. It will continue happening after. Our understanding has been refined and extended and eventually superseded by something more complete. The Sun does not need to be understood. It needs only to burn. But we needed to understand it. That need is one of the defining characteristics of the kind of mind that evolved on the third planet of this system. A mind that looks at a fire 93 million miles away and is not content to merely be warmed by it. A mind that builds instruments, launches rockets, endures the years of engineering and iteration and failure and correction required to send something into the fire's edge and asks, what is actually happening in there? Parker's solar probe answered that question. Partially, provisionally, with important details still awaiting resolution. But it answered it. It went there. It came back. It changed the map. The cause and effect chain that began with Bengt Edlund staring at spectral lines in 1941, lines that should not have existed, lines that implied temperatures no model could explain, has now been traced, link by link, to its origin. The chain runs from those spectral lines to the theoretical work of Eugene Parker in 1958, from Parker's predictions to the confirmation of the solar wind by early spacecraft missions in the 1960s, from the solar wind's confirmation to the slow accumulation of evidence that its fine structure and its origin remained mysterious, from that mystery to the decision to build a spacecraft that could enter the corona directly, and from that spacecraft to the data, the switchbacks, the funnel jets, the wrinkled Alfvén surface, the current sheet particle acceleration, the CME inflows, that now constitutes humanity's most complete and observationally grounded understanding of the nearest star. That chain did not end with the mission. It continues. The data from the December 2024 encounter is still being analyzed. The fourth annual Parker Solar Probe Science Conference, held at Johns Hopkins Applied Physics Laboratory in Laurel, Maryland in May 2025, brought together researchers still working through the deepest encounter datasets, still finding new structures, still refining the energy budgets, still tracing the connections between what the probe measured inside the corona and what eventually arrives at Earth's magnetosphere. The mission's future, its extended operations, the possibility of additional close passes, the longer-term planning under NASA review, remains open. The spacecraft is still flying. The story is still being written. What can be synthesized at this moment in that still unfolding story is the structure of what has been learned, the shape of the understanding that Parker Solar Probe has made possible. The sun's corona is hot because the sun's convection zone is churning. The convection zone's churning stresses the magnetic field. The stressed magnetic field undergoes reconnection in the funnel structures at supergranule boundaries. The reconnection releases energy as heat, as plasma jets, and as Alfvén waves. The heat warms the low corona. The jets rise into the corona as jetlets and contribute to the solar wind's mass and energy. The Alfvén waves propagate upward, depositing additional energy through turbulent wave particle interactions. The solar wind, the fast wind from coronal holes, substructured by the supergranular convection cells from which it emerges, accelerates outward, crossing the Alfvén's surface and becoming free-streaming plasma. The switchbacks born in the funnel reconnection events travel with the wind, carrying the solar surface's fingerprint outward through the inner heliosphere. The heliospheric current sheet, separating the two magnetic hemispheres of the solar system, is crossed and recrossed by Parker probe at close range, revealing particle acceleration through magnetic island merging that was previously invisible from greater distances. And the solar wind, structured and variable and carrying all of these signatures of its origin, eventually arrives at Earth, at the magnetosphere that deflects it, channels it into the polar cusps, lights the aurora, and occasionally, during major storms, shakes the ground-level infrastructure that civilization depends upon. That is the chain. Each link is now observationally constrained. Not every link is fully closed. The energy budget's finest details, the slow wind source structure, the kinetic scale physics of the final energy transfer. But each link is grounded in direct measurement rather than theoretical inference alone. That is the difference Parker Solar Probe made. The sun you see tomorrow morning is not the sun that Galileo watched from his garden in Padua in 1610. Not because it has changed in any meaningful way. The sun is almost perfectly stable on human timescales, but because the category of understanding you bring to it has changed. The light that touches your face when you step outside is not simply electromagnetic radiation from a distant fusion reactor. It is the outward expression of a system of extraordinary complexity and dynamism, a system whose finest details have now been measured imperfectly and incompletely, but genuinely, by a machine that flew into it and came back. The corona, invisible to the naked eye, burning above the photosphere at temperatures that thermodynamics seem to forbid. Heated by the continuous small violence of magnetic reconnection in structures tens of thousands of miles across. That corona is present every day, whether or not there is an eclipse to reveal it. The solar wind flowing outward from it is present every day, interacting with Earth's magnetosphere, sustaining the aurora, occasionally driving storms that affect the technology of modern life. The switchbacks threading through the inner heliosphere, carrying the fingerprint of funnel reconnection events at supergranule boundaries, are present every day, winding their way outward through the solar system on trajectories that eventually carry them past Mars, past Jupiter, past the orbit of every planet. All of this was always happening. None of it changed because we observed it. What changed is our relationship to it, from ignorance to knowledge, from mystery to mechanism, from a star observed at a safe distance to a star touched, however briefly, by something we built and sent. That relationship is, at its core, what science is. Not the accumulation of facts, though facts accumulate. Not the construction of models, though models are built and refined and sometimes overturned. But the closing of distance, the movement from wonder at what is unknown to engagement with what is real, from the spectral line that should not exist to the spacecraft that goes to find out why. Parker's solar probe closed a distance of 93 million miles, minus 3.8. It did not close the remaining 3.8. That gap, between the closest a machine has been and the surface of the star itself, remains and may remain permanently beyond reach. But the territory it traversed changed everything. The corona is no longer what it was. A bright mystery visible only during eclipses, explicable only in broad theoretical strokes. It is a measured place, an observed place, a place that humanity has been, in the person of its instruments, and returned from with data. Eugene Parker, in the final years of his life, was sometimes asked what it meant to have a spacecraft named after him. He tended to deflect the question. He was a physicist, not a mythologist, and the naming of spacecraft was not his natural territory. But he did say more than once that the most important thing about the mission was not that it bore his name, but that it would answer questions that had tormented him for more than 60 years. Questions about where the solar wind came from, about why the corona was hot, about what the inner heliosphere looked like at the scales no previous instrument had resolved. He lived to see the first crossing of the Alphen surface. He lived to see the first data from inside the corona. He did not live to see the December 2024 encounter, the deepest, the fastest, the closest to the star he had spent his career studying. But he lived long enough to know that the distance was closing, that the instruments were working, that the data was real. That is worth something. Not everything. The science is not complete. The story is not finished. The chain of cause and effect is still propagating forward, into new findings and new questions. But it is worth something in a civilization that tends to measure progress in product cycles and quarterly returns, that a man spent 60 years on a single question, saw the mission designed to answer it launched in his lifetime, and died knowing that the answer was arriving. Science moves at its own pace. It does not accelerate to meet deadlines. It does not simplify to fit the available attention. It takes the time it takes, 60 years, sometimes more, and it produces understanding that is genuinely new, genuinely grounded in evidence, genuinely capable of changing the map. The map has changed. The corona is not a mystery in the way it was. The solar wind's origin is not a conjecture in the way it was. The Alphen surface is not a theoretical boundary in the way it was. The switchbacks are not unexplained anomalies in the way they were. None of these questions are fully resolved, but all of them are fundamentally different questions than they were before August 12, 2018, when a Delta IV heavy rocket lifted off from Cape Canaveral and sent a small heat-shielded spacecraft toward the sun. The sun rose that morning. It will rise tomorrow. And somewhere between those two risings, in the 4 years of close encounters and the nearly 700 papers, and the ongoing analysis of the deepest data ever collected from inside a stellar atmosphere, something new entered the human understanding of the star at the center of everything we have ever known. If this changed how you think about the sun, about the fire that has warmed every morning of your life, about the wind that flows invisibly through the space around you, about the corona burning above the photosphere in the light of every eclipse, then the time was well spent. Thank you for staying.